This is tutorial number 21 of OMFIT and OMAS in our series. Today I'll tell you about how we're using OMAS to map experiments data to IMAS. So I prepared a few slides just that, so that we can be, on the same page, and also to remind myself what I want to talk about. So this is kind of follow-up from the DIII-D Friday Science meeting that I gave, I think 2 weeks ago now. If people want to get more information about OMAS, I put there the website, and there is the link to the Friday Science meeting presentation. And in that meeting, we kind of gave an overview of kind of at a high level how OMAS works for mapping the experimental data into IMAS format. And just as a reminder, the punchline of that presentation was that we were using the data mapping inside of OMAS to basically achieve what we have here on the right. So gather the data from the native experimental databases and serve them to OMFIT or to any Python interpreter as ODSs. So what I'll try to show in this hour is, let's pretend that we have a new device. We call it my tokamak. And let's pretend that we want to map some magnetics data from the native experimental database to IMAS, again, using OMAS. So this is, for example, if you want to do magnetic equilibrium reconstruction. I think the minimum set of quantities that you would want to do for a magnetic equilibrium reconstruction would be the polydel field coils, the magnetic field, flux loops, the magnetic flux, and the plasma current, and the toroidal field. The toroidal field. So that's too much to cover in a tutorial, and probably that would be also redundant. So we're just going to focus on two items, the plasma current and the polydel field coils. And the plasma current is just a signal, but for the polydel field coils, we want to know also kind of where the coils are, and then we will have the time traces that we want to map. So if you want to try this at home, you will have to have your own installation of OMAS and use that installation, whether you're doing it in OMFIT or, again, in your own Python interpreter. So you'll have to git clone, go to that directory, and install it, so that when you start Python, you're actually using the OMAS version that is in the directory that you cloned. Okay, so in the OMAS directory, there is a machine mappings folder, and so there are the mapping files. So there is a JSON file and a PY file for the different machines. So this is what I will try to do. We should just briefly look at what the DIII-D JSON and DIII-D PY look like, and just to point out that there are two different ways of doing these mappings. One is by writing direct MDS plus TDI expressions for the individual signals, or we can write Python functions, which are in the PY file. And once we do that, we can kind of choose what level of granularity these Python functions should have. Should we have a Python function for each individual signal, or we want to make a Python function that gathers multiple data at once? And then to get started, we're just going to start from the sample data here, and we're going to kind of strip it out and kind of start from zero. So let me go here. This is the OMAS folder. Hopefully people can see. as we said, under machine mappings, we have a bunch of files. And so in the JSON file, this is kind of what tells OMAS where to look for the data once the user asks for a specific location in the IMAS data structure. And so things that have a double underscore, these are kind of properties, if you want, of these of the specific machine. And here you can see for different quantities, the mapping can be done in Python. So here we tell it what Python function to call, or let me find one, or it can be a TDI expression where we write MDS plus expressions that are going to be evaluated when we request a certain element in the IMAS data structure. Okay. So as I said, let's start with some sample files and take it from there. So I'm gonna make a copy of these and I'm gonna rename it, as I said, as my talk. Sure. And then we're gonna do the same also for the PI file. So again, this is just some sample data. So what we can do is we could strip this out selectively of the things that we don't want. So like this, probably these options can be empty. We will have to define an MDS Plus server for our custom tokamak, and we're going to use the D3D one. And then this is some information about how to determine the COCOS convention that is used for certain signals. I won't go into that right now. So, we could actually hose it. So this is kind of a very extremely stripped down version of this JSON file, basically absolutely minimal. And then if we look at the .py, here we see, let me do, because I was playing with this. So let me do like this. Okay. So here we see how these mappings for using Python functions work. We have, here is a sample Python function. It accepts our ODS as an input pulse and some arguments. And then this is where, the association of the data is done. So if we try to run this script by itself, it will actually run all of the machine mapping functions defined in this file. And it will automatically populate for us the JSON file. So let me just do this as an example. Okay. So we will develop our own functions. So this is just to show what's happening. This routine run machine mapping functions does exactly that. It runs all of the machine mapping functions, which are defined with this decorator. And so here you see that the sample function was run, and the JSON file got updated because we added the dataset description IDS properties comment is done here. So if I go here, now I see that the dataset description IDS properties comment has been added, and this user argument is also defined. The default value of this user argument has been defined. Okay. So I think enough of kind of the details of how this works. Let's now do this for some real data. So I'm going to clear this out again, and and we will write our own function here. So let me go here. I think we've done that. We've done all of what we said we're going to do here. Let's start by so let's look at the plasma current. And as I said, this is we're just going to use the MDS plus TDI expressions directly. So where does this data go? In doing all of this, OMFIT is not required. Let me start my OMFIT. But it does help you doing many things. So let me take it from here. It appeared on my other screen. Okay. So let's look at, we said we were going to populate the magnetics IP. So for people who are not familiar with the IMAS data structure, this could be helpful. So there is a new menu here in OMFIT that says OMAS. Here we can browse the data structure, and we're going to look at magnetics. So here we have the IMAS data dictionary. If we look under magnetics, under IP, here we see that there are different plasma currents that can be stored in IMAS. I think based on the different method that the plasma current is calculated. But for today, we're just going to focus on filling out the data and the time. So the data will have to be in units of ampere, and that time is always in seconds in IMAS. Okay. So let's do this naively at first, and I'm just going to copy the expression here. I could type it in, but it's just quicker. So let's go to our JSON file, and let's. I should have copied everything. And here we're gonna tell it that and make this bigger. That whenever we request the magnetics IP data, we have to call the MDS plus TDI function ptdata2 and get IP, the IP signal, and here we pass the pulse. This is how things work for DIII-D. Because a lot of DIII-D uses this PT data storage that MDS Plus has access to. So things may change depending on the tokamak that you're working on. So let's try to use this data mapping. And as I pointed out here, I purposely do this a bit wrong so that then we can see the errors and that we see that come up, and we will correct it. Doing these data mappings, requires a bit of attention, and so I think this way, hopefully, people see kind of the kind of problems that may or the things that people have to pay attention to. So let's copy this. Let's go in OMFIT, for example, and let's access. So here we're gonna start our ODS equal ODS, and then we're gonna access the machine data, my tokamak. We've given it a shot, and then here we are trying to access the data of IP. Okay, so fingers crossed. Okay, so here we're going to we have an error, and it says, you're trying to access IP, but you haven't told me what is the COCOS convention that you're using. Okay, so well, let's go fix that. So we're going to go here, and we're going to say COCOS IO. And this changes depending on the tokamak that you're working on, or even the diagnostic that you're looking at. And so for D3D, it's 1. So COCOS stands for Coordinate Convention, and it basically defines how what is the convention with which the toroidal and poloidal angles are defined. And something like IP, the sign of IP depends on that convention. And so there are numbers that identify, there are unique numbers. There's a paper by Olivier Sauter, which basically identifies 16 possible COCOS convention, and ITER uses convention number 11. And so, you know, this is kind of its own separate topic, but, you know, when you do these kind of mappings, if the data, the sign of the toroidal and poloidal angle depend on, if your data depends on the sign of the toroidal and poloidal angle, you should know what COCOS convention you're using on your tokamak. So let's run this again. And here we have to tell OMAS that the mappings have been updated. So here we go, and we say reload experiment mappings. And then we run this again. So here we get another error, and it says, please specify the number of structures for magnetics IP. Okay, so the problem here is that we haven't told the mappings how many IP there are defined. And so here we're basically saying there is only one, the number of IP defined is only one, okay? And that one is the one that comes out like this. If you know, we could have assigned multiple definition of IP here. That's something that is that IMAS allows, and you know, we just have to work with the flexibility that comes with IMAS. So I think most tokamak will have one here, and we define one here. So OMAS, and we reload the experimental, and we run it again. Okay, so now this is taking a second. I'm running on my laptop, so we're actually creating a SSH tunnel to the MDS Plus server on for D3D, and we're accessing the IP data. So now we have another problem. So the data that we have retrieved has this length, okay, but it doesn't fit in the how do you say? It doesn't fit in IMAS, because the data type, the data size should be the you know, the array of the current, but it should have also one more dimension, and that this dimension should be just one, because of this extra you know, placeholder, or this extra arrays of structure that can occur here. Okay, so that's an easy fix. Basically, here in our TDI function, we just add one extra dimension. We only have one, so you know, we just have to add this square bracket. If you had two ways of evaluating your current, you would do something like this, and you know, this would put, you know, would populate you know, method 1 and method 2, for example. Okay, so let's fix that. Okay, so we finally were able to get our data, and we just get a warning. This is not a killer, but we should fix it. We're missing the coordinate, so we're defining the data, but you know, if the coordinate over which the data is defined is missing, I think it's good that we get a warning. So let's go fix that. Here we can probably copy this, and we're gonna assign time, and we're gonna do this by doing dim off. This is NDS plus, so I guess you need to have a bit of proficiency with NDS plus TDI functions if you decide to use the TDI approach. And that should be it. There is still a small error, but I want to address that too. So let's try this, and actually now we can plot things as a function of time. So now finally we have our time, and there are a couple of kinks that we still need to fix. As we said, the time should be in seconds, not milliseconds. So here we see that 10 to the 3 D3D works with milliseconds. And then also we got another warning that it should be that the IP time shouldn't have COCO specified. So let's fix both of those in one pass. So time shouldn't have COCOs, and we shouldn't use milliseconds, but we should use seconds. Okay. So let's reload, and hopefully we get no warnings, and the data looks as what we expect. Okay, 10 to the 6, it's amperes, which is what the data should be. The data should be in amperes. Okay. So hopefully people were able to follow that. And again, in the end, this is what we ended up with. Okay. So now let's look at the toroidal field coils. As I said, there are two pieces to this. There is the hardware and there is the signals. People can choose, however, to populate the ODS, make things as granular as they want. But I think what we've done for D3D could be a good model. So we just go ahead and start by copying the PF active hardware function from D3D and move it to my toke, and then we'll see how we can use if your tokamak has a EFIT. You probably have these mhd-in.dat files that define the location of the magnetics and the coils. And so we can use OMFIT to get that information and paste it over in our mapping functions. So let's start with that. Let me get the D3D.py. And again, we're looking for PF active. So we have a PF active hardware and a PF active coil current. So we're going to start with this one. We're going to copy it here, and we're just going to host the sample one that we had. Okay. So here, what this function does is it has hardwired the location of the, I think it's 18 toroidal field coils that are on D3D, and it has the number of turns, and then there is a function that David Eldon wrote to basically take these tables and assign it, and these tables with the location of the coils in R, Z, their length in R, in Z, and the tilt in 2 angles, and populate the ODS. These functions, like these PF coils to ODS, they're in this common.py, which are functions that could be shared among different tokamaks. Yeah, we were here. And then, so this function will take care of defining the geometry of the polyidal field coils. And then we're gonna fill out the name of the coil, the identifier, and the number of turns. Again, also in this case, we could go here, OMAS, browse the data structure, PF active. So under PF active, coil 0, we said name, identifier, element, and element would be 0 for us. And here we have the geometry, which could be oblique or rectangle, I guess in most situations. And so that function will take care of filling that out for us. And the turns with the sign. Okay, so let's start by running this and as is, and then I'll show you how to take the information that you have in your MHD in .dat if you're using IFIT, and how you can use that to change these numbers. So let's just run it. So here I'm just going to run my toke, and here, so what this again, run machine mapping functions, what it does is it runs the function that we tell it to run. Here it runs all functions. If we want to run just one function, we can just tell it to run this function. And basically it looks at what data gets filled when this function is called, okay? And so then it goes back to the JSON file and it populates it for us, so that we don't have to do this tedious job by ourselves. Here, if someone is trying to access the PF active coil element geometry rectangle R, call this Python function, so this is, we could do this by hand, but this saves us a lot of typing and also a lot of mistakes. So how do we populate these numbers? So again, OMFIT is not necessary, but it can come to the rescue for something like this. For example, my talk MHD. So if you are using IFIT at your institution, you have some MHD in .dat, and here we're using OMFIT to pick that file. I'm just going to tell it to go on the IRIS server and just download it. We're going to load it as with the OMFIT MHD in .class, and just put it in the OMFIT MHD in. So that's again, it just needs to create the SSH tunnel once to gather that file. Okay, and so here we have this MHD in .dat file with the data inside. If we double click it, we see the coil configurations and the magnetic probes and flux loops and so on and so forth. So if we want to, so one could go and take by hand each one of these quantities and copy it over. There is a function called pretty print that we can use. And this one prints the data in a, in a reasonable way, organized by the different coils, vessels, and flux loop magnetic probes. And so for the polyidal field coils, we just copy this. We would come here and we would paste it here. So the number of Polarized field coil may be different for your device. Uh, Here, I took D3D and pasted it over D3D, but uh, the the principle stands. And for the number of turns, uh, I don't exactly know what is this FC turn, which is all one, but what we want to take is a turn FC, which is the number of turns of the polarized field coils. Uh, and Again, and we want to copy this over like this. Okay. And then for uh, um, D3D, there is a logic for assigning these the names of these polarized field coils as they're numbered, and so these polarized field coils will be called F A 1, 2, 3, 4, 5, 6, 7, 8, 9, and then FB, and then 1 to 9. Okay, so that should do it. Again, it's easy if you have an MHC in that and you're running OMFIT. Otherwise, you'll have to find your own way to populate this. And we can look at what we've done here. So, for example, so there are different ways of looking at what we have populated. So one way is to call the Python function directly. So we could do that. So we do ODS equal ODS, um, and this. So if we look here under ODS, we have all the data that this thing this function has populated. We see that these are rectangles and so on. The other approach is to well, we could plot the data. So we can plot the data. This is plotting from the OMAS data structure. I think we can even plot it this way. Yeah, plot PF active overlay. We plot it. And so the other way is to access the data dynamically with this width environment, which basically tells it, if you're trying to access data and and the ODS doesn't have data in memory, then try to go fetch it by looking at the mytok mappings. So that's the other way to do this. So let's do it here. I guess copy and pasting from PDF gives me those artifacts. So ODS equal ODS. So this is an empty ODS. So it doesn't have anything. But when we ask it to plot something, it will get it should have done it. It didn't do it. ODS open plot PF. What am I doing wrong? Okay. I don't know why. Huh. I'll have to check that. Okay. Or we can dynamically explore the data like this. And I hope this one will work because okay. So I don't know why this one plot PF active overlay. Well, I'll have to see why that is not working. So here under magnetics IP, and it has the Aha, I know why. I need to reload my experimental mappings. Okay, so let's try this again. Yay, okay. Moment of panic. Okay. So yeah, this one loaded that if you have your mappings up to date, right? It should know that when you're asking data for the PF active geometry, where to get it from from the MyTalk mappings. The last way is to just open a ODS, not inside of a width environment. This will leave this ODS. Um, what this will do, it will keep a link to your mappings, and basically whenever you're asking something that it doesn't have, it will know where to get it. And so here we see everything that we've mapped, the dataset description, which is always there, the magnetics IP. So here you see that pause, it went on MDS Plus and fetched the data. And then the PF active coil. So this is a way, if you open a device, for example, DIII-D, and you look at the shot, this one will show you all that is available for that shot, for that machine. So and data will be gathered as you try to see it. So wall description to the linter. When I get to the point that I need to see the data, then that's when MDS Plus gets called and the data gets retrieved. Okay. So we've done the hardware. Let me go back. Still have 20 minutes to make the hour. So now let's do the same. It will be very similar for the signals. Let's take PF active current data and customize it. So we're going to take this and move it over. Okay, so now for the signals, okay, so for the actual current that flows into those coils, we want to know, well, what the coils are, and we want to know what is the name of the coil so that we can go in MDS Plus and fetch it, okay? So this is how it's done for DIII-D, okay? And let me walk you through this. So to start, we're gonna call the PF active hardware function to figure out what are the coils that we need, that are defined in our tokamak. Okay, so this is the function that we just worked on, and this function wants to have a ODS as an input. Now, what we want to do is so one could have done naively, could have done this. Okay, and this one would have worked, but it wouldn't be ideal because now when we run the PF active coil current data, right? When we run it here, this machine mapping function will write in the JSON file, okay, that you have to call PF active coil current data to get the geometry, okay? And we don't want that because, if I want the geometry, I don't want to fetch the data. So I think there is a value in keeping them separate, okay? So we want to use the hardware function to get the geometry, and then the coil current data to actually do the MDS Plus calls. So so what we do is this unwrap function removes this decorator from the PF active hardware function. Okay, so what you need to know effectively is that if you have a function in here that's calling another function that you have defined, you want to call it with this unwrap. And then we don't want the data of this function to go pollute our ODS. So we just make another ODS and we put the data there. Okay, so that's the reason for why these things are done like this. And then for D3D, well, I think for any tokamak, we have this fetch assign function, which it's designed to call MDS plus in the most efficient way, which is basically do just one call to MDS plus, telling it all the signals that we want to get. And then we're just going to get, so we make just one request, we get all the data back in bulk, and then we do the assignment. So again, we could run this, but let me pretend that we are going to do this kind of by hand and see how that will work. And then, you know, provided that this is the most efficient way of doing it. So what we want to do is that we're going to do for channel in now we have ODS1, and the list of channels is this PF active coil, and then what we want to do is we want to know what is the signal that we want, the MDS plus signal. So this one will be here. ODS1. Okay. So let me comment this out, and let's try to run this and see what we get. Print channel signal. Okay. So if I run this and I made a mistake, so in Python 3 there are these f strings. So they allow you to evaluate a variable in your local namespace just by putting f and then a string. And this is actually fairly convenient when working with you know, with ODSs, and if you're using this this way to access the data. Okay, so here are you know, channel number and the signal that we want. The TDI expression, which is what we're going to use for MDS plus, it's defined here. So let's do TDI is equal to this, and this is where the data will need to go. So we want to do ODS. I can leave the print here. So we will have to assign time and data. Okay. So we're going to have a TDI expression for the data and a TDI expression for time. Name of 0. People can see. Okay, so now to assign the data, we're just going to do MD as value. We have to tell it a server. We're going to use the D3D server. We have to tell it an MDS plus tree, just the top level tree for all of D3D will work for us for this. We have to give it a pulse, and we have to give it a TDI expression. So for time, it will be TDI time, and then we're gonna get just get the data, and then data. Okay, so This is probably the naive way of assigning the data. We can try to run it.
Wait,
Yeah, mistake.
your TDI time and data need F.
Yes, excellent. Okay, so now if we run this, again, this will have to generate the SSH tunnel, and then it's going to go and access, access the data and put it into the ODS. And what this function does, the machine mapping function, it also turns on some debugging that tells you what you're accessing in NDS Plus and how long does it take, which is useful. And so if we look at my.toc.json, here we should find PX active coil. Let's look at .data maybe. Okay. Yeah, so for PF active coil current data, we have assigned, we're going to call this function, okay? So notice that here the Cocos IO is 11. We could change it here, or the other way is that we use the OMAS environment to define what Cocos we're using. The PF coils again need that information. So we're just going to say with the OMAS environment, ODS, Cocos IO equals 1. So, and basically what this does is it says this ODS inside of this width environment, all the data that I'm giving you is in Cocos 1, and OMAS internally will take care of doing the conversion from whatever Cocos we're defining to whatever Cocos, well, to Cocos 11, which again is the IMAS Cocos. Okay. So this is our naive approach. We can do it. We can uncomment this, run it, and what this does is, again, it just does it, but it does it with a single MDS plus call, which makes it more efficient. Okay. We could even, yeah, I don't want to drag this too much, but maybe it's worthwhile just seeing how this works. Effectively, what we want to do is we want to make a list of TDI functions, like expressions that we will want. So we want to do TDIs, and then here we can just say TDIs append, and we can do TDI time, and then the same for data. So the first loop, the first loop is basically figuring out what are all of the MDS plus things that we need. Okay, and then we will have another loop where we do the assignments, and in between we will have to query MDS plus. So if we say results, instead of TDI time, now we just tell it all of the TDIs that we want. Okay, and now here we're gonna query. Okay, so so the logic, which again, you can see, if you're curious, you can go into this fetch assign. It's basically figure out all of the MDS Plus signals that I need, do a single call to MDS Plus with this list, and then we're gonna assign the data the by accessing these results. So hopefully this one doesn't bomb on me.
I suspect you need to subscript TDI time and TDI data in your results by using like an enumerate or something on the for loop.
No, so results fetched all the different TDI time and TDI data. So you see here I have DMOV, PT data, F1A, and then did I screw up?
Oh, no, you're right. I was looking at the wrong thing.
Okay. Yeah, F2A. Okay, yeah, no, it works. So so figure out the signals, query the signals, assign the signals. Okay. So like before, let's see what we have accomplished. We could add, we could call the function by itself that we've made. So if we go to OMFIT, we can call, whoops, we can call the two functions that we've made. This one will take a little longer now because it has to go and fetch the data in MDS Plus. So we have PF active coil, current, data, and time. And you see the here the time, right? So if I plot time and data, it's again, it's a millisecond. That's, that's why it's a good idea to go. There's a lot of, I don't want to fix that. Let's just use the let's just use the official function, which has the time normalization, the data normalization here. So let me reload the experimental mapping. Let's do this. Yeah, and now time is in seconds. Okay, which makes me happy. Or let me see. Or like we did before, we can dynamically load. So once we have the data in the ODS, we can plot it. So if we go plot PF active data, this is the data that we fetched for the different coils. And or once again, we could dynamically open this. So something like this. Oh, this one was DIII-D. My talk. And now under PF active coil, if I want to go see the current, it will take time to go fetch the current, right? Okay. So that should cover most of it. Where are we going with this? The reason again why we're doing this is to if we can have the data from different machines all mapped into the IMAS format, this can be used to generalize our OMFIT workflows and the generation of the inputs for different codes. So, for example, if we want to run IFIT for an SDX or a new machine, DIII-D, what we would do is we would have to generate the equilibrium constraints from the data that we have loaded into the ODS. which is what we're going to do here. And then once we have the equilibrium constraints in IMAS, we can take those equilibrium constraints and generate a K file, which is the input to IFIT. So IMAS has a placeholder for equilibrium constraints. And so we've written a function in the OMAS physics library of functions that takes the equilibrium magnetics information, and in the future we'll do also MSC and other constraints, and populates the equilibrium constraints elements in the IMAS data structure. So let's do that. So let's copy this. Let's go here. The ODS is already there. It's dynamically loaded. So I think I can simply do this. Here we have some equilibrium constraints. This is, my talk is effectively DIII-D. So these are the times at which we're going to make those constraints: 1, 2, and 3.3 seconds. So if I run this, now we see that we have equilibrium that has appeared under time slices. We have the 3 time slices that we selected. And under constraints, we have the IP constraint and the current and polyidal field coil constraints measurements. If we go here and we do plot, I think, for example, the PF active data. So this is in color are the actual time traces, and this is the constraints that would be and the dots are the constraints for an equilibrium code. Now, if you're not using IFIT, but you have an equilibrium code that can take data from IMAS, your code should be able to take these current constraint, polyidal field constraints. For DIII-D, we have a whole set, like all of the magnetics constraints are defined. And so you should be able to take those and run your equilibrium code based on that. And once you have that done, then you'll be, for if you're running IFIT itself is not coupled to IMAS yet. It cannot read data directly from IMAS. And so the approach here is to generate a K file from the data that we have in from the constraints that we have in the ODS. And so, for example, we would this is still actively in development, but the approach would look like something like this, where we generate an empty K file, and then we use this. We define we tell the OMFIT KQDK class in OMFIT populate my K file from the data that I have in my ODS. Right. So this one requires knowing something. For example, here we have to know this one failed because it needs to know the radius at which the vacuum field is defined. So let me do that for our tokamak. 1.6995, which is DIII-D. Okay, and so here in the K file, for example, we have for our MyTok, we have the plasma current, and we have the constraints for the polyidal field coils. And yeah, once you map more data to IMAS, you'll see more elements in the K file being populated.